So in this section, we're going to look at methods that we can use to assess or validate our models. The method used generally just predominantly depends on what type of prediction was produced. So whether it was categorical or probabilistic or continuous. So that's how we're going to classify or distinguish these different metrics. So if you work in remote sensing, you may be familiar with the concept of the confusion matrix or error matrix, or contingency table. So the idea here is that we're comparing the category that was correct versus what it was classified or called. So in this example, we have 6 classes and different proportions in each of the blocks. So the proportion in this block represent the proportion of samples that were forested and were correctly classified as forested. Whereas, for example, these ones were forested but were misclassified as developed. For a couple other examples, these cells were crop but were misclassified as pasture grass. So the diagonal represents the correct classifications and all the off diagonals are incorrect. So the nice thing about an error matrix, it doesn't just give you a sense of the overall accuracy of the model or prediction, it also gives you a sense of what classes are being confused. From an error matrix, there's multiple measures that can be calculated. The simplest is the overall accuracy, which is just simply the number of features that were correctly classified divided by the total number of features times 100. So if you had 800 validation samples and 81 of them were correct, then you'd have an 81% overall accuracy. In the next slide we'll look at users and producers accuracy, which breaks down the components of error for a specific class. So one of the issues with the overall accuracy is it doesn't really tell you where the confusion is. So we have to have other measures at a class level. Okay, so users accuracy is a measure of commission error. It can be thought of as the probability that a feature classified on the map actually represents that category. So it's the number of features of a specific class correctly classified divided by that row total, so summing down across the row. In contrast, producer's accuracy is a measure of omission error, and it's the probability of a reference feature being correctly classified. And now we're just taking the number of correct features for that class divided by the column total down the column as opposed to across the row. So users is a measure of commission error, producers is a measure of omission error. And we'll look at a table in a minute to discuss those in a little bit more detail. Okay, the kappa statistic is another common statistic used in remote sensing and also just to look at categorical predictions. So sometimes you can just get a sample correct by random chance. So for example, if you had an area that was 80% forested, you could classify everything as forest and it'd be 80% right, even though that's basically useless. So kappa offers a means to adjust over accuracy based on chance agreement, and you can see the equation here. So again, that's a common metric to use because it takes out that component of getting something right just by random and adjusts for that. So it offers, again, just an adjustment of overall accuracy. Okay, so let's look at a couple of other examples of error matrices. So as you can see, the producer's accuracy show up here at the bottom. They were a measure of omission error, right? So the reference data represents the column. So if we were looking at something like forest, these cells represent cells that were supposed to be forest, but they were supposed to be forest, but they weren't called forest, so they were omitted from that class. So again, producer's accuracy is your omission error. Whereas if you look at look across the rows and a user's accuracy, that's your commission error, right? So these samples were incorrectly included into the forest class. So they're, again, commission error. So producers down the column, omission error. Users across the row, commission error. And again, one of the great things about the error matrix is that it's not just an assessment of overall accuracy, but can give you a sense of where there is error. So for example, there was 15 samples that were supposed to be cropland that were misclassified as pasture grass. So that seems like there's a lot of confusion between those classes. There were 17 samples that were developed but were incorrectly classified as water. In contrast, there were no forested samples that were incorrectly classified as barren. So it gives you a sense of class level accuracies. Here you can look at how classes vary in terms of, again, omission and commission error rates. Here's another example. This is just a simpler one where we have two classes, forest versus not forest. So again, these are your incorrect labels and then your correct labels. So again, this is your omission error. So 6 samples were omitted from the forest class. And then this is your commission error. 15 samples were incorrectly included in the forest class. Okay, so if you want to calculate or produce a confusion matrix in R, there's a couple different ways to do it. Probably the easiest is to use the confusion matrix function that's provided in the caret package. So to run that function, you simply have to provide the predicted class that is an output from the model and the actual class from the original validation data, and it'll produce for you a table with some associated summary statistics. Next, you could also just do that for the training data. So again, you're really not supposed to assess on the training data, but you might want to just see how well it's doing on the training data. So you can call confusionmatrix.train to get the output from the training model. Another package that is useful for this is the the epidisplay package, which provides this cap function, which is used to calculate kappa from a table. Okay, so precision recall on the F1 score are some common other measures that you'll see if you deal with categorical predictions. So let's first, before we get into that, we need to understand the difference between the true positive, false positive, true negative, false negative designations. So imagine we have a classification where we're trying to differentiate yes versus no. All right, so the true positive rate would be things that were predicted as yes that were yes, so they were right. The true negative rate would represent samples that are no and were correctly predicted as no. So it's similar to error matrix. This diagonal is the correct number, or the correct classifications. And then the false negative are ones that were predicted as no, but they were actually yes. So again, that's a false negative. So if you were trying to, say, find tumors in medical imagery, that would be like missing a tumor. And then the false positives are things that were predicted as yes, then were actually no. So that would be saying this is a tumor when it actually wasn't. So from those different summations, we can calculate some things. So precision is simply the true positive, not the number of true positives divided by true positive plus false positive. Recall is true positive divided by true positive plus false negative. And then the F1 score is basically combining those. So it's 2 times precision times recall divided by the sum of the two. So those are common measures that we see, again, for classification. And you see the sum in like deep learning and object detection. We also may see the term sensitivity. That's effectively the same thing as recall. And specificity, which is true negative divided by true negative plus false positive. So if we were looking at this, if we have true positive plus false positive, that would be an example relative to the yes class of the omission rate for precision. And then recall, we have true positive and false negative, so that would be similar to commission for the true class. Okay, so now we're going to move on and look at measures that are used for assessing continuous predictions. Probably the simplest would be RMSE, or root mean square error. If you're a GIS or remote sensing person, you may have ran into this in the context of assessing georeferencing output or the positional accuracies of points or the accuracy of like elevation measurements like from LiDAR. So RMSE, or root mean square error, is this. So you take the correct value and subtract from it the predicted value. So the correct minus the predicted is known as the residual. So you're basically calculating the residual. So you take the residuals, you square the residuals, and then you sum them up, divide by the number of samples, and then take the square root. So it's basically a sum of the squared residuals divided by the number of samples and then taking the square root. So let's say, for example, you were trying to predict parts per million, so like a chemical concentration. So it would be parts per million minus parts per million, so it would still be in parts per million units. If you take the square of that, you end up with parts per million squared. If you take the square root, then you're going to end up with parts per million again. So RMSE is just going to be in the unit of measurement of whatever you were predicting. Mean square error is basically just RMSE, but without the square part. So in that case, the units would be the square of whatever the units were, so parts per million squared, for example. Generally, you tend to see RMSE used more often than MSE, partially because the units are more interpretable. Okay, so another common method we use to assess a continuous variable is R squared. So R squared is a measure of the proportion of variance in Y, or the dependent variable, the thing you're predicting, that is explained by the model. So how that's calculated is you have to get a measure of the total variance, and to do that you take the total sum of squares, which is effectively just each value with the mean of the data set subtracted. So that's a measure of variance once you square it. So if you sum all those up, you end up with the total sum of squares, right? So it's the sum of the squared variances. So again, think of that as a measure of the total variability in Y. And then the residual sum of squares is the variance that was not explained by the model. So here you're basically just switching out the mean with the predicted values for each sample. So you're basically calculating the residual, squaring it, and summing them. So if you take the total sum of squares and you subtract from that the residual sum of squares, what you have left over is the sum of squares for the model, or the variance that was explained. And if you take the variance that was explained and divide it by the total variance, then you get back the proportionate variance explained. And that's effectively what R squared is. So if you explained all the variance in the model, you would get back a value of 1. If you explain none of the variance in the model, you get back a value of 0. It's scaled from 0 to 1. Higher is more variance explained, or a better model. Okay, another kind of caveat to this is if you have multiple predictor variables, multiple x's, such as in multiple regression, or if you're using multiple predictor variables with your machine learning, then you have to adjust R squared because generally R squared is going to increase if you add more predictor variables, even if the model isn't really improving. So this is the equation to do that. So effectively you subtract this from 1. So R squared is R squared. N is the sample size, so the number of samples, and then P is the number of predictor variables. So that offers an adjustment when you have multiple predictor variables. The Akaike Information Criterion, or AIC, is another measure for assessing a continuous prediction that takes into account both the strength of the model and the complexity of the model. So measure relative quality of statistical models for a given data set. Lower values indicate a better model, again in terms of predictive power and limited complexity, and you can use this to compare different models. The AICC, which is the corrected AIC, is a different version where you correct for having a finite sample size, so like not a lot of samples to create the model. If you're interested in calculating RMSE and R, I would recommend the metrics package. So it has functions for calculating MSE and RMSE and some other measures, and it's very easy to use. So here's an example. To get RMSE, you just throw at the actual values and the predicted values, and it'll throw you back an RMSE, based on those numbers. And here's a link to the documentation for that specific package. Okay, so our last tool for assessing it that we're going to specifically look at is ROC curves are receiver operating characteristic curves. And these are commonly used for assessing probabilistic predictions as opposed to continuous or categorical predictions. So this is based predominantly on the true positive rate. So again, that's the proportion or rate of the samples that were true and were called true versus the false positive rate, which is the proportion of samples that were actually false but were called true. So let's look at that in terms of a graph. So imagine this is the distribution of the false samples, and this is the distribution of the true samples. So if we were to put in a probability threshold cutoff, we could separate these curves into different components. So if the cutoff were here, the true positives would be the portion of the curve ahead of the line. So this part of the curve that ends here. So those would be samples that were true and were called true. The false negatives were things that were called false that were actually true. So that would be this lower portion of the first curve, the true curve. And then the false curve would be this. So true negatives would be this purple area here. So they were negative and they were called negative. And then the front of that curve would be your false positives. So this blue area that extends back behind the red area here. So they were negative, but they were incorrectly called positive or incorrectly called true. So the comparison between true positive rate and false positive rate will actually vary based on where you put the probability cutoff or threshold. So when we create an ROC curve, instead of picking a threshold, we effectively just move that back and forth and create a variety of measures across that spectrum. So here's the curve. Again, you're looking at specificity, which is the true positive rate. So that's your x-axis, sensitivity, which is your true positive, which is your y-axis. Sorry, I looked at the wrong axis there. So true positive rate, and then your specificity, which is 1 minus the false positive rate. So the higher the curve is, the better a job is doing at creating this probabilistic prediction. If you looked at the total area in this space, since it's a scale of 0 to 1 and 0 to 1, there's 1 times 1 or 1 square unit of space, right? So if this curve completely hugged this line, it would maintain the entire volume of the graph and would have an area of 1. If it's smaller than that, it's going to be less than 1. So what we actually generally use from this curve to actually assess models is a measure called the area under the curve, or AUC. So this is the area under curve. So it's effectively the area under the ROC curve, and it's scaled from 0 to 1. So imagine again this volume is 1, so you're summing up all the area that falls under this curve. Now if you had a curve that fell on this 1 to 1 line, then it would take up half the graph space, so it would have an area of 0.5. And that's effectively the same as a random guess in terms of probability. So if you had a 0.5, that's a really bad model. And as the curve gets further and further from the line, your predictive power in terms of, again, probabilities is increasing. So again, if you have values from 0.9 to 1, that's considered excellent. 0.8 to 9 is good. 0.7 to 8 is fair. So in short, this is interpreted very similar to a grade scale. So we're generally hoping to get AUC values above 0.8, hopefully even above 0.9. Okay, so if you wanted to actually calculate these types of curves in R, I would recommend the PROC package. So here are some examples of functions from the PROC package. So there's the ROC function, which requires the input response, and then the predictor class will return the ROC curve data. That data can then be plotted using the plot.roc function. AUC function will calculate the AUC value from a specific ROC result. And then if you wanted to compare two models based on their AUC values, you can do the ROC.test function, which offers a statistical comparison between models in that space. Okay, so that's it for the section on model on model assessment. Now we're going to look at just some specifics about improving models through a couple different means.